Welcome to the lecture on non-isothermal flow considerations in Tundish. So, we talked about so far the mixing and related phenomena inside the Tundish, and in that we did not consider the isothermal flow considerations, especially that happens when there will be change in the density, and because of that you will have the change in that source term. So, especially it will be we will be talking about those conditions when you will have the natural convection type of conditions will be occurring. When we solve the energy equations. So, how those things need to be taken into account, and which are those dimensionless numbers which are required to be kept in mind while we talk about the similarity conditions. So, in this lecture we are going to discuss about that. Now, before that we have already discussed that we try to maintain the similarities. We have the geometric similarity, we have kinematic similarity, we have dynamic similarity. So, we come across the different conditions we have we get. So, especially we get the Reynolds similarity as well as the Prof similarity because of the different type of forces which whose ratios we try to keep same between the model and the prototype. So, based on that we come across few dimensionless numbers. One is Reynolds number and that is Prof number. So, Reynolds similarity, it will be important in laminar flows. However, it becomes less important when there is turbulence. So, and also what happens that in the water modeling, when we do the isothermal flow conditions, in those cases the three forces which are mainly there, inertial and gravitational and viscous forces. So, that gravitational force will be not affecting that flow field. So, what happens we have seen that using that two similarities, if you maintain the Reynolds similarity, you have if you try to maintain both of them, then you have to keep the the model and prototype size as the same. So, that is what we have studied earlier. But Prof similarity criteria, what is to be noted is that it will be giving a convenient method of modeling the melt flow and aspects of inclusion, collisions and flotation in the Tundish, because whenever you have those considerations where you have the buoyant effects into considerations, in those cases this so the effect of gravitation will be there. So, in those cases when you do the inclusion flotation kind of modeling and all that, in those cases these Prof similarity criteria will be providing a convenient method, because the particle inclusion particle which is going inside, now that is subjected to these buoyant forces. And also when we talk about the temperature conditions, when we talk about the difference in the temperature because of the either the heat transfer or the the different temperature of the inlet stream from the ladle. So, when that comes, so in the continuous casting Tundish steel making, many a times your conditions may become non-isothermal. So, because the temperature may not remain the constant, temperature may change, and these non-isothermal nature of that flow, it may be due to the heat losses that is taking place from the top surface through the walls, through the bottoms. So, from all these places you have these heat transfer taking place, heat losses being taken place, and also in certain cases what we see that the temperature of the inlet stream which is coming into the Tundish. So, even that may be that may vary from the from heat to heat. So, suppose in one case the ladle has emptied and in that case the ladle is moving out and another ladle will be coming. So, so the ladle which is coming now, that is the new ladle, that may have the different temperature, and or maybe with time in the same heat also the temperature may change, because the ladle is continuously giving the liquid metal, and slowly in the end there may be change in the temperature. Now, because of these change in temperature there are certain changes, there are certain considerations need to be taken, certain similarities need to be maintained. And what are those extra terms which come into picture when we non-dimensionalize these governing equations, especially the Navier-Stokes equation or the temperature equation. So, that will be basically interesting to know. So, there may be difference in the temperature of the inlet stream from the ladle and that of the molten steel which is present in the Tundish. So, that is what I told you, that there may be difference in those temperature which is already there in the Tundish, and that when the metal is coming from the new ladle. So, there will be changes in the temperature, and this change in temperature is basically that will be affecting these flow structures, flow patterns inside the Tundish, and they will be different than the isothermal conditions, and that may be this is quite possible during that continuous casting process, because in that you have continuous movement of liquid steel and you have continuous changing interchanging of the ladles. So, so in that case you need to satisfy the thermal similarity in addition to the geometric and the dynamic similarity, and for that basically you need to see those criteria, that how you will manage that. So, what happens that if you go for the momentum balance equation for the turbulent flow conditions. So, for that your equation becomes like you have dou of rho v j and that is rho v I divided by dou t, and then you have the convective term. So, you have rho v I v j and divided by dou of x j. So, that is your convective term. Then on this side, other side you have the diffusive term. So, you will have dou of dou x j, and then you have the being the turbulent flow, you get the effective value of the eta, and then you have dou v I by dou x j plus dou v j upon dou x I, and then you get the pressure term, that is dou p by dou x I, and then an extra term which you get will be because of the change in the density as the temperature will change. So, that will be rho minus rho reference, and then it will be multiplied with G I. So, this is the extra term which is basically this will be accounting for the buoyancy term, buoyancy force that will be per unit volume. So, you have all these terms we have already seen, that these are the what are these different terms which what they indicate and all that. So, so rho and minus rho difference, so that will be your change in the density. Now, if for the fluid, if the beta is the coefficient of thermal expansion. So, if beta is coefficient of thermal expansion of the fluid, in that case what happens that you can express beta will be nothing but the change of the density. So, you will have minus 1 by rho reference, and then that will be dou rho by dou T. So, at constant pressure. So, that is what the expression for beta will be, thermal expansion of the fluids, that is at constant pressure. Now, if you have very small variation in the density, so then you can write, because that way you will have rho minus rho reference here. So, this rho minus rho reference will be minus beta times rho reference into delta T. So, for small variation in density, you can write this is rho minus rho reference, and this will be basically minus of beta times rho reference into delta T. So, that is what you can write when you have the very small variation in the density. Now, we can write in place of the rho minus rho reference, we can write this minus of beta rho reference delta T, and then Gi. So, that term will come here, and so accordingly we will write the equation dou of rho V I upon dou T plus then you will have dou by dou x j, and you will have the rho V I V j. So, that will be convective term. Then you will have the diffusive term. So, that for that you will have eta effective, then dou of V I by dou x j plus dou of V j upon dou x I, and then we have the pressure term, and then as we discussed, it will be from here it will be rho minus rho reference will be minus of beta rho reference delta T. So, it will be minus of rho that is beta, then you have rho reference, and then you will have delta T and then Gi. So, that is what you get when you incorporate this term because of the change in density, that buoyancy term. Now, if you write this equation for the temperature, so for the conservation of thermal energy, your equation will be becoming dou of rho Cpt, and then it will be by dou T. So, that will be this is dou T, and then you will have the dou of rho and Cpt Vj, that is your convective term, divided by dou xj. So, it will be dou of by dou xj, and it will be K effective and dou T by dou xj. So, this is again the effective thermal conductivity. It will be for the molecular as well as for the eddy component in the case of turbulent flow. So, that is what these two together they will be governing the dynamics of the flow inside the Tundish. Now, if we try to write, so before that we will have the also the boundary condition, and the boundary condition at the inlet will be T. So, that is T is T inlet. So, that will be your boundary condition. Now, if we try to write the dimensionless form of this equation, so your both the equations can be dimensionally in the dimensionless manner. It will be written, and few non-dimensional parameters will be cropping up in that case. So, if you try to write the non-dimensional form of this equation, so you will have again the equation coming up. So, dou of rho star, then you have Vi star upon dou T star. So, then it will be plus again dou of rho star Vi star Vj star. So, this is the second term, and by dou of x j star. So, that will be equal to again dou of dou x j star. So, you are non dimensionalizing, and then in that you will have the eta effective divided by rho reference into V n and L. So, that term will be coming, and you will have dou V star. So, dou V I star by dou x j star plus dou V j star divided by dou x I star. So, that will be here, and then you will have minus of dou of p star by dou of x I star, and lastly we will have the term beta delta T L by V square, and then you will have G I. So, if you non-dimensionalize these equations, so this V square term will be coming here, and then this is one of the another number that we will discuss, that what is that which is what are those things which are coming to picture. Then if you do the non-dimensionalization of the thermal equation, thermal energy equation, so that will be coming dou of rho star T star divided by dou T star, and then you will have dou of rho star T star and V j star divided by dou x j star. So, that will be equal to dou by dou x j, and you will have this time you will have the term that will be coming is k effective by rho reference C p and V and L. So, that will be coming as because of this non-dimensionalizing of the equation, and then you will have dou T star upon dou x j star. So, this way you will have these two equations as the one. So, we are basically non-dimensionalizing the equation T star. So, we are taking that as T minus T naught upon T inlet minus T naught. So, that is how you get these non-dimensionalizing of the equation. So, you must have some idea about it. So, so we are getting non-dimensional numbers, and what that non-dimensional group which we are getting from here, one is the eta effective upon rho reference V L. So, this is nothing but if you look at this, so rho V L upon eta, so that is the reciprocal of the Reynolds number. So, and also it is effective values, this is for the turbulent flow. So, this is nothing but the reciprocal of the turbulent Reynolds number here. If you look at, so you will have eta effective and divided by rho reference V L. So, this is indicative of the turbulent Reynolds number. Similarly, if you look at the further a number, what you see this number beta delta T naught, and then you will have L, and you will have G I. So, and divided by V square. So, if you look at this number, this is another number which we are getting, this dimensionless group, and this is suggested by the researcher Damle and Sahai. So, they got they have invented this number, and that number is known as the Richardson number, and this is basically known as the Tundish Richardson number. So, that is indicated by Tu. Then if you look at this number k effective and divided by rho reference C p V into L. So, if you look at this, this is nothing but if you look at this is the reciprocal of. So, this will be one is rho C p by k, and then you will have. So, it's basically it can be taken as the reciprocal of the product of the turbulent Prandtl number and turbulent Reynolds number. So, basically what you see that these three numbers come into picture when we try to study these non-isothermal conditions in the case of the Tundish flow. Now, this number beta delta T then L and this G I upon V square. So, as we discussed, so it is nothing but it is the ratio of the buoyancy force to the inertia force, and that is why this number is it's taken to be the number which is very much considered for maintaining the similarity when we are talking about the non-isothermal conditions in the Tundish. So, this number, that ratio of the buoyancy force to the inertia force. So, that needs to be that is Tundish Richardson number. So, the Damle and Sahai, they told that under these conditions, if you maintain that similarity, if these are taken as that criteria, then in that case the flow behavior which is predicted even by the water modeling. So, it may be treated as the similar ones as will be done experimentally or with the RTD investigations. So, that is what that this is needs to be considered, especially in the case of the natural convection or the non-isothermal case, especially you will see when you do the modeling. In those cases, you will see that as compared to the non-isothermal case, you will have the changes in these flow fields. When you will see that there will be change in the temperature. So, when you do that case study, when you are doing the case of suppose ladle changeover process, or even in during that process itself, when you are doing the transient analysis, in those cases as the time progresses and if the temperature will be changing. So, because of that there will be change in the density, and that may lead to the change in the flow field that needs to be considered. Now, as I was discussing that why what were those findings which were suggested by the Damle and Sahai basically. So, they investigated on the water modeling as well as on the numerical investigation also, and they found that why we are talking about these even turbulent conditions. So, when they did the experimental studies on two kind of the Tundish, and the one of the Tundish was taken bigger, another was taken the smaller one, and then accordingly they did the water modeling studies. So, they did the pulse input. So, they have shown that they took two cases, one was A and another was B, and A was 60% of B in size. So, that is what was the case, and they varied the flow rates in the two cases, and B was as you see that B was larger, and they they did that pulse input study for a range of the flow rates, which is inflow rate into the Tundish, and then they found the studies, and what was seen that for A and B normally the RTD curve was seen to be very close. So, basically suppose if you talk about the work which is done by the Damle and Sahai. So, they have taken the suppose A's length was suppose 0.8 meter and B's length was 1.35 meter. So, it was basically 60%. So, L is ratio of the length is 0.8. Similarly, you have the depth or the width they also have. So, in all these length cases you have that lambda is taken, and then you have so when they did, in that case what they saw that as we discussed, that you will have in both the cases they are getting the so they have done for many cases, and actually they got the flow fields very very close like that. So, when the flow rate or the it was changed from 0.13 to 0.76 liter per second. So, this was for A, and the top height is going close to 0.58 or so, this is 0.6. So, dimensionless concentration was measured, and this is time. So, this is dimensionless time and this is dimensionless concentration. So, what they found that this is time of suppose 0.5, then 1, 1.5, then you have 2. So, like that it may go up to 3. So, 2.5 and all 3. So, for A they have got, and for B also they got a similar type of curve, and it's going like that, except for so they have got that range in which all these 0.132. So, in that case they have seen so it was varied from 0.13 to 0.88 liter per second, but only for the case of 0.13 liter per second, that they saw that this is for 0.13 liter per second. So, what they saw that when your Tundish is bigger and you are keeping the flow rate as the minimum one, in that case only, otherwise these ranges were the same. So, the on these RTDs here it was even closer to each other, here they were somewhat sparse, but only one of the line which is the for the minimum of the flow. So, that was seen to be having a larger peak little bit, and the peak was observed to occur little early, and then it was going into so it was decreasing, and ultimately it has matched with the line later. Now, this was only seen. Now, the reason for this could be attributed to the prevalence of the non-turbulent conditions, because you have a larger Tundish, and this is for 0.25 to 0.88 liter per second. So, that was the value. So, so that may be because of the the laminar type of flow condition, which might have been the cause for these changes. So, so that is what was basically found by these researchers. So, so just to tell you that these water modeling as well as the mathematical modeling results have been proved to be matching with each other when the flow is turbulent. So, in those cases they seem to be validating each other. So, that is basically the experimental work can be used as validation for the numerical investigation if you are doing further on a particular geometry. So, that is these are the considerations that needs to be taken when you are going for the water modeling in the case of non-isothermal conditions. So, we will talk about other aspects in the Tundish flow in our coming lectures. Thank you very much.